to briefly introduce our speaker. Hyungjin Kim received his PhD in 2017 from Korea Advanced Institution of Science and Technology, and currently serves as a researcher at several groups of detached electron synchrotron. He conducted his postdoctoral research at the Weizmann Institution of Science between 2017 to 2020. Professor Kim focused on the study of elementary particle phenomenology, with particular emphasis on the understanding the nature of dark matter. So let us warmly welcome the Professor Kim to give us a report. Please start your speak.
Yeah, so first of all, thank you very much for a kind introduction, and also thank you for inviting me to your online seminar series. Today, what I'm going to talk about is the fluctuations of ultralight dark matter and related phenomenology. And before I go into the detail, I want to start by giving you a brief overview of ultralight dark matter searches. And so from there, we can build on to the fluctuations of ultralight dark matter. Before I start, I want to begin with defining what I mean by ultralight dark matter, because in the literature, ultralight dark matter is used to represent different kinds of dark matter candidate. So before I start, it's good to define what I mean by really ultralight dark matter. So in this talk, I will use a ultralight dark matter and wave dark matter interchangeably. And what I mean by ultralight dark matter and wave dark matter is any light bosonic dark matter whose mass is smaller than 10 eV scale. What is so special about this ultralight dark matter is that their occupation number is much larger than 1. So occupation number is, roughly speaking, the number of particles within one wavelength of dark matter. And as you can see in this expression, once the mass of the dark matter becomes smaller than 10 eV scale, now we can see that the occupation number grow rapidly, so that this allows us to describe these kind of dark matter as the collection of classical waves rather than collection of individual particles. This is a rough definition of wave dark matter, and depending on the theoretical matters for the dark matter, they may only interact with the center matter through the gravitational interaction, or they may be interacting with center matter through non-gravitational interaction. And how they are interacting with standard matter through the non-gravitational interaction, that really depends on underlying theoretical matter of wave dark matter. So if we think about axions or axion-like particle, the way that these particles, these dark matter couples to standard matter is, for instance, they can couple to gauge boson through this anomalous coupling. They can also couple to Fermion currents through the derivative couplings. They can also couple to, in certain cases, in the case of QCD axion, they can couple to nucleon electric dipole moment in this way. And depending on which coupling we're looking at, there are a variety of possibility for potential method for search for this kind of wave dark matter candidates. So if we think about axion coupling to the photon, there are traditional microwave cavity experiments, and you can also look at some of the astrophysical system to look for the signal of wave dark matter that is specifically coupled to FF dual. When it comes to axion coupling to nuclear spin, there are other possibilities. We can use magnetometers or co-magnetometers or NMR, nuclear magnetic resonance, to search for this kind of dark matter. And individual of them is probing and constraining certain part of this parameter space, where x-axis is the mass of the dark matter and y-axis is the coupling constant to the nuclear spin. And if we think about their coupling to nucleon electric dipole moments, the fact that they are dark matter and the fact that they are coupling to electric dipole moment, what's going to happen is that because of this coherent oscillations of dark matter, they are inducing a oscillations of nucleon electric dipole moment. So by looking at the harmonic oscillations in nucleon electric dipole moments, we can prove a certain parameter space as shown is in this parameter space in this figure. And moreover, if we are considering QCD axion where they are coupling to phi GG dual, they couple to gluon field in the standard model, there also could be quadratic coupling of axion to pion, and also quadratic coupling to nucleon mass and nuclear G factor. And because of background dark matter oscillation, what it does is that they are inducing a oscillations of atomic energy level so that one can in principle use atomic spectroscopy or interferometry to search for the same parameter space. This is the parameter space for the light QCD axion. There are other theoretical possibilities for the wave dark matter. We can think about spin 1 dark photon dark matter, or we can even think about scalar dark matter, where each of them couples to standard model in a distinctive manner. For the dark photon dark matter, one of the options is they couple to standard matter through this kinetic mixing portal. And in this case, there are similar kinds of searches like haloscope, but there's also other astrophysical system that we can look for dark photon dark matter. For the scalar dark matter, they can couple directly to the field strength tensor as shown in this figure. And in that case, simply because they are changing the fine structure constant, they are similarly changing the atomic energy level such that you can use for instance, atomic clocks or other atomic spectroscopy to look for this kind of scalar dark matter candidates. Roughly speaking, so far the discussion is summarizing wave dark matter searches based on a non-gravitational interaction. So we have seen that depending on theoretical possibility, they couples to standard model in a distinctive manner. And depending on which coupling that we are considering, there are variety of options for wave dark matter search. Now what I'm going to do is that I'm going to switch gear a little bit and discuss gravitational interaction of the wave dark matter and the behavior of wave dark matter on the galactic scale. And we're going to discuss how we can search for wave dark matter whenever they are only interacting through the gravitational interaction. So this is something that I'm going to discuss for the rest of the talk. So I want to start by introducing one of the well-known numerical simulations of ultralight dark matter. This is done by these people like roughly 10 years ago. What they did is they are simulating the ultralight dark matter on the cosmological scale. So in the panel A and B, what you see here is large-scale structure simulations of fuzzy dark matter whose mass is 10 to minus 22 eV scale compared with the cold dark matter. And you see that on the larger scale, their structure is more or less similar, but in the case of ultralight dark matter, there's a little less number of smaller structures. And if we look at one specific galaxy, as you can see on the figure right-hand side, there's also something interesting happening in terms of density profile. So in the cold dark matter case, through the n-body simulation, we know that the density profile is likely to be Cosby NFW profile. But in the case of ultralight dark matter, there is a characteristic solitonic core at the center of the galaxy. And outside of the solitonic core, the density profile is looking very similar to NFW profile, which is something that is observed in the n-body simulations of cold dark matter. This is an interesting feature, but this is not the end of the story. So this is the density profile averaged over a certain time scale. But if we look at actual time evolution of this numerical simulation, there are much more interesting things going on. So if we look at this figure in the left bottom side of this slide, This is a snapshot of the numerical simulation. And if we look at the one galaxy, we see that there's a central solitonic core at the center of the galaxy, bright spot. And outside of the solitonic core, there is a repeating patterns of bright spot and dark spot. Here, the color code means the density. So bright spot and dark spot means that there are order one density fluctuation that is happening all of the galaxy. And this is not the single only simulation that see this kind of feature. There are many other subsequent simulation, numerical simulation that has observed a similar kinds of behavior of ultralight dark matter. So in these two simulations, there is a solitonic core at the center of the galaxy, and outside of the solitonic core, there is order one density fluctuation, as you can easily see in these two figures. So this density fluctuation, order one density fluctuation, is an interesting characteristic feature of ultralight dark matter, and there are several interesting phenomenology on the galactic scale coming from this density fluctuation. So let's now try to understand this density fluctuation better. One of the most intuitive way to understand this density fluctuation, at least to me, is to think of them as some sort of quasi-particle. So instead of think of them as a random density fluctuation, I'm going to now think of them as a quasi-particle whose size is given by the wavelength of the dark matter, which is given by 1/m times velocity of the dark matter. And their effective mass is given by the total includes the mass within the volume of the wavelengths. So these are the size and the effective mass of this quasi-particle, which represent the density fluctuation. And as you can see here from this expression, they depends on the particle mass, the small m here. So depending on the particle mass, their size and the effective mass could take astronomical value. So for instance, if we think about 10 to minus 22 eV scale, the effective mass could be larger than 10,000 solar mass, whereas their size could be 100 parsec scale or even kiloparsec scale. If we go to 10 to minus 16 eV scale, the effective mass of this object could be a mass of some of the heaviest asteroid in the solar system, whereas their size could be, roughly speaking, 10 AU scale, which is the size of the solar system. If we go even higher, then the effective mass, for instance, we are thinking of 10 to minus 11 eV scale. The effective mass could be 1,000 kilogram, whereas the size will be 1,000 kilometers. So this mass is, roughly speaking, the mass of elephants. So there are quasi-particle of the mass of the elephants that is floating all of the solar system and also all of the galaxy. So the concept of this quasi-particle may seem naive, and this is not really a particle in a traditional sense, but it's still very useful. It provides a very useful thinking tool in order to understand the behavior of wave dark matter halo, as well as their interaction with the stellar object like stars or planets or other massive object in our galaxy and other galaxies. So let me demonstrate how we can understand the behavior of wave dark matter with this quasi-particle picture. So I want to start by trying to understanding the order one density fluctuation in the wave dark matter halo. And in order to do that, I want to start from particle dark matter halo. So particle here, I'm just imagining 1 GeV scale wind-like particle dark matter halo. So this is a dark matter halo. And what I want to do is I want to zoom in and kind of split the box into very small cubes, like this green box, where the size is given by 1 centimeter. So if I ask the number of dark matter particle in each green box, then the average number of dark matter particle in green box is order 1, because now I'm assuming 1 GeV scale dark matter, and I know the density of the dark matter to be 1 GeV, roughly speaking, 1 GeV per cubic centimeter. So average number of particle in each green box is order 1. And because this is a particle, the number of particle inside of this green box, they follow a Poisson statistics. which means that their mean value is given by this expression, and bar is, roughly speaking, the rho times the volume of the box. And the variance is also given by the same quantity. So now we can ask, what's the density fluctuation over these small boxes of the centimeter size? So in this case, since I choose this small box such that the average number is equal to 1, the density fluctuation over this small volume is, roughly speaking, order 1 in the particle dark matter halo. But if we choose instead much larger box, say I choose a box where its size is given by 1 AU, now the average number of dark matter particles in this box becomes much larger. This is going to be 10 to 39, and their statistical property is the same, but since the average number is now very large, the density fluctuation over this AU-sized box is very small. So in the particle dark matter case, if we ask a question of what's the density fluctuation over the size of AU scale box, they are very, very, very small. But in the case of wave dark matter, ultralight dark matter, we are thinking of them as a quasiparticle. And the size of the quasiparticle, as we have seen, they can be astronomical size. So if I think about 10 to minus 15 eV scale, the wavelength of this quasiparticle is 1 AU, which means that on average, there is an order 1 number of quasiparticle in this AU-sized box, so that the density fluctuation, order 1 density fluctuation over this larger scale can be naturally understood in the context of this quasiparticle picture. And there are many other things that we can do with this quasiparticle picture. So what we did here was just trying to understand order 1 density fluctuation with the quasiparticle picture, but we can also try to understand the way that they interact with the stellar object in the context of the quasiparticle. So in the fuzzy dark matter or in the wave dark matter halo, as we have discussed, there's an order 1 density fluctuation just floating all over the simulation box or in the galaxy, and they are interacting with the stellar object, planets and stars, and they are changing the way that the stars are orbiting around the galactic center. So we can try to understand the interaction between wave dark matter and the stars. And as a particle physicist, the easiest and simplest way to do that is just draw Feynman diagrams. And since we are talking about gravitational interaction, there's only one kind of the diagram between the wave dark matter and stars, which is given by this one. There's a one graviton exchange. This is the gravitational interactions, and we can easily calculate the matrix elements. So if we are calculating this quantity in the zero temperature, zero density background, I can calculate the matrix element in this way. And through the Born approximation, we can calculate the potential between wave dark matter and the star given by this way, in this way. So this is nothing very special. This is just long range force, 1 over r. And G here is a Newton constant. Small m is the mass of the dark matter. Large m here is the mass of the star. But we're not talking about zero temperature, zero density QFT. We're talking about dark matter halo. So there are many dark matter already in our dark matter halo in other galaxies. So if I repeat the same calculation in the background of dark matter, what we can see is that there's always some occupation number enters in the expression. So in the case of matrix element, there is another, roughly speaking, another factor of occupation number. So if I do the same Born approximation, I can calculate the potential between these two objects, but the result is multiplied by additional factor of occupation number. So if we recall the definition of occupation number and effective mass of quasiparticle, we can repackage this expression for the potential in terms of Gm, m effective over r. So we can understand the interaction between a wave dark matter and the star as if they are interacting, as if this is an interaction between quasiparticle, massive quasiparticle, and star, so that we can recycle the classical expression for the potential simply by replacing the particle mass to the effective mass of the quasiparticle. And again, this is a very heuristic argument, but we can in principle go through more complicated calculation. We can use kinetic equation like Boltzmann equations or Landau equations. And after going through all the complicated integral, what we see at the end of the day is more or less similar to what we discussed heuristically. It's up to factor of few. So there are several interesting phenomenological implications of this interaction between wave dark matter and stars. The wave dark matter interaction to the star can change the behavior of the stellar evolutions in two ways. And one of the ways that the wave dark matter can change the motion of the star is through the dynamic reflection. So what is this dynamic reflection? I want you to imagine a homogeneous dark matter medium. So here I'm just considering particle like dark matter. And I want you to imagine a one star that is moving in a one specific direction. And because of the gravitational interaction between dark matter and star, there is attraction of dark matter towards the trajectory of the star. So naturally, there's a little bit of overdensity of the dark matter behind the trajectory of the star. And this overdensity is kind of dragging the motion of the star and slowing down the motion of the star again. And this is called dynamic reflection. This force, this additional friction force is called dynamic reflection force. And this is already calculated 80 years ago by Chandrasekhar. So there are several different components going into this expression. There's a dark matter mass, and there's some logarithmic factor because of the logarithmic divergence of gravitational interaction, because this is a long-range force. So we have to impose a maximum and minimum impact parameter. So the maximum impact parameter here, Bmax, is roughly speaking the size of the system, and the minimum impact parameter is the minimum impact parameter where the approximation that goes into the derivation of this dynamic reflection breaks down, or the size of the dark matter. So because of this dynamic reflection force, they do something interesting to the stellar orbit that is orbiting around the galactic center. So even though we start from perfectly circular orbit of the star around the galactic center, because of this dynamic reflection force, the star, the orbital energy will be continuously dissipated away. And at the end, they are spiraling down to the center of the system. So their orbit decays to the center. So after a certain time scale, they will all go into the center of the system, in this case, center of the galaxy. And it has an interesting phenomenological implication. So what you see here is a Fornax dwarf galaxy. This is one of the dwarf galaxy around the Milky Way. And what you see in the little circle is the globular cluster. This is a cluster of the stars. And they are orbiting around the center of Fornax dwarf galaxy. And from this dynamical friction calculation, we can, in principle, estimate the time scale, orbital decay time scale, in which each of the globular cluster falls into the center of the system. And in the case of cold dark matter, there are a few globular clusters where the orbital time scale is less than 10 gigayears, whereas they are still orbiting around the Fornax dwarf galaxy far away from the center. And this is kind of giving us puzzles, why they are still orbiting far away from the center, especially when the orbital time scale is less than 10 gigayears. This is often called Fornax globular cluster timing problem. And in the case of cold dark matter, there are some globular cluster that is kind of puzzling, given that their orbital time scale is less than 10 gigayears. So now we can study how this picture changes in the case of ultralight dark matter or wave dark matter. So as we discussed in the quasiparticle picture, what we can do is we can recycle the same expression for the dynamic reflection simply by replacing the particle mass to the effective mass. And also now a quasiparticle have a size. So the Bmin, the minimum impact parameter, is replaced by the size of the object, size of the quasiparticle, which is given by the wavelengths of dark matter. So what it does is this replacement of minimum input parameter with the wavelengths of the dark matter, they are kind of suppressing the dynamic or friction force such that they are lengthening the orbital time scale. So if we redo the calculation of this orbital time scale for the fuzzy dark matter, ultralight dark matter, their orbital time scale is a bit larger compared to cold dark matter, so they can partially alleviate this Phonax globular cluster timing problem. And this is one of the interesting phenomenological implications of interaction between wave dark matter and the stellar object, in this case, globular cluster. Another interesting way in which wave dark matter can change the motion of the star is through randomly heating the star. I mean, there will be random stochastic interaction between quasiparticle and star, and this random interaction will change the orbital parameter in the random way. So if we consider some sort of bound stellar object like a star cluster, it is possible that through the quasiparticle and star interaction, it is possible that the quasiparticle wave dark matter inject energy into the stellar cluster. And when it happens, when there is an energy injection into the stellar cluster, what's going to happen is that because now they have more kinetic energy, so that their structure will expand. They becomes larger and they becomes puffier. There are several interesting phenomenological implications of this quasiparticle stochastic heating. They may resolve star cluster, they may change the velocity distribution of the stars in a certain system, they may perturb galactic disk or other stellar substructures. So in this work done by these people, they study the star cluster in Eridanus 2 dwarf galaxy. And because of this quasiparticle heating, at some point, if the wave dark matter mass is around 10 to minus 20 V scale, the quasiparticle heating is too large so that they become incompatible with the observations of properties of the star cluster. So they were able to constrain certain part of mass for the ultralight dark matter. And also, in some of the dwarf galaxies, the stellar velocity dispersions are well measured. And simply because of the same reason, if there is ultralight dark matter and if there is an energy injection into the stellar population, at some point, if the mass of dark matter is roughly speaking 10 to minus 20 V scale, the observation becomes a little bit incompatible or inconsistent to the theoretical prediction in the presence of ultralight dark matter. And there are also recent studies done by these people. They also study the evolution of the star cluster in the presence of ultralight dark matter and comparing the size and the property of this object with the observations of star cluster in ultra-faint dwarf galaxy. And in that way, they were able to constrain a fuzzy dark matter mass, which is roughly about 10 to minus 19 eV scale. So this is another way in which wave dark matter can interact with stars and change their evolution in the galactic scale. So these are based on quasiparticle heuristic arguments of quasiparticle picture. And now I want to go a little bit deeper into the wave dark matter and their statistical property, because by understanding the statistical property of wave dark matter, we can achieve a better understanding of wave dark matter and their behavior on the galactic scale or on the subgalactic scale. So in order to study statistical property of wave dark matter, I want to start from a very basic field theory. So in the first two chapters of any quantum field theory book, we quantize a scalar field. And when we do that, we expand the field in terms of creation annihilation operator. And there's also mood function or wave functions this way. And here I'm using discrete index notation. And here the index represent any quantum numbers. So for the wave function, it's nothing but the solution of Schrödinger equation or Klein-Gordon equation in the relativistic limit. But we are talking about non-relativistic dark matter. So this becomes a Schrodinger equations. So depending on particular system, if we think about homogeneous medium, this will be given by plane wave. If we are thinking about certain system where there is a gravitational potential, the wave function will not be given by the plane wave. But solving for wave function is straightforward. Only thing that we have to do is solve this Schrodinger equation. And what about this creation and annihilation operator? Since we are talking about dark matter halo, in order to specify the statistical property, we have to specify the density operator of the system. And the density operator is simply the direct product of density operator of each mode. And the density operator of each mode is given by this one, where P is a quasi-probability distribution. And here, bracket notation, this quantum state here is the coherent state. So what I mean by coherent state is this is an eigenstate of annihilation operator. So once you apply annihilation operator, what they do is that they spit out a complex number, alpha I. And once we have these density operator and this expansion of the field, we can in principle calculate all the correlation functions of ultralight dark matter field. But if you find this is a little bit too complicated and confusing, we can do a much simpler version of that. Instead of thinking of them as an operator, we can simply replace this creation annihilation operator into the complex random number, alpha and alpha star, where their underlying distribution is given by this quasi-probability distribution. There are many heuristic arguments why this has to be the case, under which assumptions. But here, basically what I'm talking about by doing this is I'm basically saying that my ultralight dark matter field given by this phi hat is nothing but the Gaussian random field. That's all that I'm saying by imposing this quasi-probability distribution and taking alpha and alpha star as a complex random number distributed over this quasi-probability distribution. That's all that I'm saying in these two slides. So once we have that, we can do multiple kinds of the things. This is a basically one simple statistical description. And with this one, we can do multiple different kinds of the thing. One of the thing is we can try to understand the behavior of homogeneous wave dark matter more carefully. The second thing is we can try to understand better the behavior of wave dark matter in the solar system where there's a gravitational potential so that the wave function will be deformed. We can also try to understand how we can construct whole wave dark matter halo with this formulation without having to do the whole set of complicated numerical simulation. We can also try to understand how the wave dark matter halo is evolving adiabatically when there is a adiabatic evolution of the baryonic matter, like gas or black hole. So let me briefly discuss each of them and conclude. So first thing is understanding the behavior of homogeneous wave dark matter medium. So now we're talking about homogeneous system. So the wave function is given by plane wave. And we can simulate the behavior of wave dark matter with our statistical description of ultralight dark matter because we have complex random number. And by drawing those complex random number from underlying probability distribution, we can simulate the wave dark matter halo in this way, where you can see there's a density fluctuation over the coherence time scale. This is the same figure, and you can see that there's a large order 1 density fluctuation happening quite often in the simulation box. We can also try to understand their statistical behavior analytically because already we have the statistical description, we have quasi-probability distribution. We can calculate any correlation function analytically. So one of the things is that if we think about density fluctuation in this two little circle, they are statistically uncorrelated if their separation is larger than the wavelengths of the dark matter, because their correlation decays exponentially. We can also try to understand their temporal behavior. So if I look at the density contrast in this circle, they behave in a stochastic manner. So in one coherence time, their value is more or less constant, but in the next coherence time, their value changes in a random manner, in a stochastic manner. But there's also finer structure in this evolution. If we zoom in to the finer time scale, there are actually coherent oscillation as well, predictable coherent oscillation at the frequency equal to 2 times m, the mass of the dark matter, where their coherent oscillation amplitude is suppressed by v squared, where the v is the velocity of the dark matter. So there is a very easy way to understand these two distinctive behavior, and that way is to pretend that wave dark matter halo consists of single mode, the single mode at a single frequency. And if we calculate the energy density with the single mode, there's two terms. One term is a constant term, and this is basically representing the stochastic evolution of the density over the coherence time scale in the case of realistic dark matter halo. There's another term that is suppressed by v squared, and this is what represents this coherent oscillation, because you see that there's a cosine 2mt, so this represents a coherent oscillations of dark matter at the frequency that is equal to omega 2n. And this temporal behavior can be nicely described by their power spectrum. So we can go to the Fourier space and write it as a power spectrum. And the power spectrum, we have two distinctive components. One component is at the omega equal to 2m, and they are suppressed by omega to the 4. And this is representing a coherent oscillations of this density fluctuation. And there's a nice smooth low frequency component when the omega is smaller than m times sigma square. So this is representing a the stochastic evolution of the density fluctuation over the coherent time scale. We can also try to understand the probability distribution of the density of fluctuation. From our statistical description, we can easily calculate the probability density function of density fluctuation, and they are following exponential distribution. So we can easily calculate what's the probability of observing a density larger than certain threshold in certain patches, and that is given by this exponential form. Here is a very crucial difference between wave dark matter and the particle dark matter. In the case of wave dark matter, the density fluctuation, they are exponentially distributed, whereas in the particle dark matter, they are distributed over the Poisson distribution. So large density fluctuation in the case of wave dark matter is much more common compared to the density fluctuation in the particle dark matter halo. So this is a discussion of homogeneous wave dark matter halo. Now let's try to understand the behavior of the wave dark matter halo in the solar system with this statistical description. So in the solar system, what is happening is that there is a sun at the center of the box. So now the system is no longer homogeneous, and my Schrödinger equation becomes this form where there's a gravitational potential. So once we solve this Schrödinger equation, now we see that the wave function is no longer plain wave, but is distorted by the gravitational potential of the sun, and this is given by some hypergeometric function. But this is nothing but the free electron wave function in the case of proton at the center. So this is exactly the same form. And because of the gravitational potential, there is some kinds of focusing effect that is happening in the solar system. So in this figure, what I'm showing is the mean density contrast in the solar system. Here, I'm assuming that there's a monochromatic dark matter wave that is propagating from plus x direction to minus x direction. And as they are propagating, because of the gravitational potential of the sun, we see that there is a larger density along the downstream of the dark matter wind. So depending on the mass, there is a little bit of smoothing of density contrast. Or if you go to higher mass, there's a more sharper patterns of over density and under density in the case of wave dark matter. What does it imply is that all of the wave dark matter experiment, or basically all of the terrestrial experiment that we are doing that is performed on Earth, and the Earth is moving around the sun. Every year they are just orbiting sun once, And because of this density contrast, what we're gonna see is there is a distinctive annual modulation patterns. So here, the black dashed line is the density contrast in the case of particle dark matter. And depending on the wavelengths of the dark matter, there is distinctive patterns of annual modulation. If the wavelength is smaller than 1 AU size, then the density contrast becomes very similar to that of particle dark matter. But if the wavelengths becomes comparable to the size of solar system, then there could be larger density contrast or even smaller density contrast if the wavelength is much larger than the size of the solar system. Not only they are inducing annual modulation, they also change the spectral form of dark matter. And what we see in this figure is that there is an enhancement of velocity distribution at the small velocity tails. And the reason for that is if the dark matter has smaller velocity, they are more susceptible to be deflected by the gravitational potential of the sun, so that there is a little bit of enhancement of velocity distribution in a small velocity tails. And this is for the halo dark matter. And for the case of halo dark matter, this effect is only 3, 4, 5%. But if we think about other dark matter substructure, like stream-like object with a small velocity dispersion, or slow-moving dark matter object, this kind of gravitational focusing effect will be more dramatic, and they will provide us valuable information about the property of the wave dark matter. So now what I'm going to discuss is a possibility to construct whole wave dark matter halo with this formulation. So what we do is we expand the field in terms of wave function and complex random number. So in order to construct whole dark matter halo with this formulation, we have to start from certain density profile. And from the numerical simulation, we first make an educated guess for the dark matter profile. So we know that the dark matter profile will be soliton plus NFW-like profile. So we put ansatz for the initial density profile. And by doing that, we are fixing the gravitational potential as well. So once we fix the initial and gravitational potential, initial density profile and the gravitational potential, now we can solve the Schrödinger equation and we can calculate all the eigenmodes. Now the field is linear combination of this eigenmodes and the complex random number. Here there's a one undetermined quantity, which is of the distribution function, the F, the occupation number. In order to determine the occupation number, we calculate the mean density from this statistical description and compare that to our target density profile, our initial ansatz, and we fit the occupation number such that our mean dark matter density reproduce the target density profile. And by that way, we can fix the occupation numbers. And once we do that, we can study the property of wave dark matter halo without having to do with the complicated numerical simulation. So in this work, they were able to reproduce the dark matter profile and also some of the statistical property of the density contrast. And in this work, they were checking whether these dark matter halo constructed in this way are stable over a certain time scale. And they also calculate the power spectrum of this density fluctuation at a different radius. So this will provide very useful tool to understand the behavior of the wave dark matter without doing complicated and time-consuming simulation. So the last thing that I want to discuss before I finish is to understand the adiabatic evolution of the wave dark matter halo with this formulation. So the setup that I'm considering is following. So suppose that there is some gas cloud, the spherical gas cloud, and there are stars orbiting around the center of the system with a certain orbital radius. And because the gas is interacting through the electromagnetic interaction, they are losing energy by dissipating. They are dissipating energy into the photons, and they lose energy and they contract. And as they are contracting, they go to the center. Their size becomes smaller, smaller, and then they are compressed. And in the classical mechanics, there's a theorem that whenever the Hamiltonian changes adiabatically, the action variable should be conserved. And one of the action variable is the angular momentum. And in order to conserve the angular momentum of the star, what we have to do is that the stellar orbital radius has to be shrink according to adiabatic evolution of the gas. And the phenomenological implications of this adiabatic contraction is that as a result of this collapse of the gas, there will be a steeper stellar distribution. And here we have talked about the evolution of the gas, but it doesn't have to be the gas. It could be a adiabatic growth of the black hole. And if that happens, the stellar orbital radius has to shrink, and then this will give you steeper stellar distribution. And this is not only for the stars, it can also happen for the dark matter. If there is a adiabatic growth of the black hole or a collapse of molecular cloud, dark matter should respond and they should be compressed accordingly. And this adiabatic compression can be easily understood in the case of wave dark matter with the statistical description that we discussed in several slides ago. Because of adiabatic theorem in the quantum mechanics, whenever the Hamiltonian changes slowly, the eigenstate of initial Hamiltonian, they tends to remain in an instantaneous eigenstate of Hamiltonian throughout the evolution. What does it mean is that we calculated this mean dark matter density, and they are given by linear combination of product of occupation number and the wave function. And because of this adiabatic theorem, the occupation number for each mode will stay the same. What changes is the wave function according to the adiabatic evolution of the system. So in order to understand this better, I have a one toy example. So here, this is a hydrogen atom. I have a proton, I have an electron, and what is shown here is the ground state solution of hydrogen electron wave function. And here I'm imagining very hypothetical situation. Suppose that I change the charge of proton adiabatically. This is not a realistic example, but for the sake of discussion, let me just assume that I can do that. If I can change the charge of proton adiabatically, what's going to happen is that the wave function of electron will compress and the density will increase accordingly. So this is what's going to happen also for the wave dark matter if there is an adiabatic evolution of black hole or collapse of the molecular cloud. So in this very toy example, even though we start from initial density profile, which is just regular soliton plus NFW profile, if there is an adiabatic evolution of central black hole, the dark matter halo can be compressed, and as a result of compression, the dark matter profile at the center of the system will be much higher. And this doesn't mean to be a realistic example. This is just an example for the purpose of demonstration. In the realistic example, previously, this looks like a soliton plus kind of compressed dark matter spike. But in certain cases, the central black hole may observe a central soliton as well as some of the low angular momentum. And if that happens, the compressed dark matter halo profile will look like this way, which is something that is given by broken power law. But anyway, the adiabatic compression of the dark matter halo, wave dark matter halo, can be easily understood with our statistical description. So the last thing that I want to discuss is a possible way to test this compressed wave dark matter halo, which is through the observation of gravitational wave. So now let's imagine there's a central black hole and companion object, which is either black hole or neutron star, which is roughly about the solar mass. And whenever there's a binary between central black hole and neutron star or black hole, they are orbiting around the central black hole and they are losing energy by emitting gravitational waves. And as they are losing their energy, they spiral down. And as a result of that, the frequency of gravitational wave increase steadily. So this is kind of toy picture for evolution of gravitational wave form. But in the adiabatically compressed dark matter halo, there are other effects. We talked about dynamical friction as a way to dragging down the motion of the star. And because of this large overdensity in the compressed wave dark matter halo, these companion objects lose energy much faster than the case without compressed dark matter halo. And as a result, the gravitational waveform changes more rapidly. Their frequency increases more rapidly compared to the case where there's no compressed adiabatic halo. Sorry, there's no compressed wave dark matter halo. So what we did in this work is by looking at gravitational wave, just by looking at the gravitational wave, whether we can reconstruct this compressed wave dark matter halo. And in this work, we have identified several astrophysical benchmark where we can do that with the future LISA gravitational wave interferometers. In particular, here in this system, we consider a central black hole of the mass 10,000 solar mass and companion object of the 1 solar mass. And we consider the ultralight dark matter mass to be 10 to minus 13 eV scale. And in this particular benchmark, astrophysical benchmark, we show that it is possible to reconstruct the wave dark matter halo. And not only that, we can also distinguish a particle dark matter halo from the wave dark matter halo, or the wave dark matter halo from the particle dark matter halo. So this will provide us a way to distinguish, disentangle the nature of the dark matter, whether it's a particle or a wave, just by looking at the gravitational wave. And this is almost everything that I wanted to talk about. So we talked about fluctuations of gravitational wave, the fluctuations of wave dark matter, and there are many interesting phenomenological implications of that. Like there could be changes of the stellar motions, and we can also think about this kind of adiabatic compression of the wave dark matter halo, and potentially observing that with the gravitational wave interferometer. That's it. Thank you very much for your attention.
Thank you so much for your very nice talk, Professor Kim. And well, I think this is good time for questions. So if there is any questions for Professor Kim, they are very welcome. Well, maybe in the meantime, maybe I have well, I'm not an expert on this topic. Actually, I do particle physics regarding the B-meson anomalies, like flavor physics, really. But I'm getting interested into gravitational waves, and also, well, when doing my analysis, I'm always concerned about the statistical significance of my fittings. So I saw that at the very beginning you had a table where you were comparing the results of the model you were implemented, trying to explain this yes.
Yeah.
So I was wondering if you did any kind of if you use any kind of metric to estimate what were the significance with respect to the paradigm model and also the experimental data.
Yeah, so here we kind of did the very naive thing. So these the data, these numbers are taken from the references, and based on these numbers, we just estimate the orbital decay timescale for cold dark matter and degenerate fermionic dark matter, strongly interacting dark matter, as well as fuzzy dark matter. So here we are not trying to do the more thorough statistical analysis in order to distinguish which model is better than the other model or vice versa. We just, based on this number, we estimate the orbital time scale. And based on this orbital decay time scale, this may be a little bit puzzling still, or maybe there is a chance of this dark matter candidate resolving this kind of puzzle. But I have to say that we didn't do very thorough statistical analysis in terms of model comparison here.
I see. And for example, yeah, regarding the same data, I was wondering if how did you take just a benchmark point for obtaining the results in blue, or did you have any criteria for picking up the parameters for which you were able to obtain those numbers? And also, if you were able, if there is any possibility to improve the parameters, you know, to try to get a best fit to the data.
Yeah, this is something that I'm not 100%. I mean, I don't think I have an answer to your question. So these numbers are coming from astrophysical observation. And I have to confess that I am not very familiar with the astrophysical uncertainty that goes into these numbers. But once you have these numbers, and once you trust your analytic estimation of dynamic friction force, now calculating this number is relatively simple. You just put the numbers, and based on this uncertainty, you can calculate the number plus, plus minus uncertainty in the orbital time scale. Yeah.
Perfect. Thank you, Professor Kim. So I think I see a question in the chat. So it says from John Lin Gong. It seems that in this scheme, the dark matter should be like as low as 10 to the minus 13 electron volts. Is there any other indication that the mass of a wave dark matter is as low as 10 to the minus 13 electron volts?
Thanks for the question. So I didn't say much about the range of dark matter mass, but when it comes, so let's go back to my definition of wave dark matter. So my definition of the wave dark matter or ultralight dark matter is any bosonic dark matter candidate whose mass is smaller than 10 eV scale. So anything that falls into this category is wave dark matter. And the discussion that we did, the statistical description and everything is valid as long as the mass is smaller than 10 eV scale. When it comes to whether there's any theoretical motivation for dark matter whose mass is that small, 10 to minus 13 eV scale or 10 to minus 20 eV scale, while those kind of light axion-like particles or dark matter can easily arise from more UV setup like string theory or extra dimensional setup, their axion-like particle can easily arise. And also there are recently some interesting developments in terms of a dynamic solution to the hierarchy problem. So one example is cosmological relaxation scenarios, and there are other variety of this mechanism. And there, this kind of light bosonic dark matter is also commonly happening. So in the case of relaxant dark matter, it can be 10 to minus 12 eV scale or 10 to minus 11 eV scale. So I would say there are many theoretical models where the dark matter mass could be that light. But beyond that, what I want to say is that anything between 10 to minus 20 eV scale all the way up to 10 eV scale, there are a whole bunch of possibilities. These are a large range of the dark matter mass.
Okay, I understand that. Thank you. And my another question is that can the gravitational lensing be used to detect such a density fluctuation of wave dark matter?
That's a great question. I do not know, but that's a very interesting question. I do not know. But here the thing that we have to think about is these quasi-particle density fluctuation is happening only for coherence time scale. So these are not something that goes all like infinite amount of time. They appear and disappear over the coherence time scale. So now the question is whether you can use the gravitational lensing in order to prove this one over that short time scale. That's an interesting question. Yeah, but I don't know the answer to your question, but that's definitely worth thinking about. Yeah.
Oh, thank you.
Okay.
Maybe another question is that you mentioned that you can use the gravitational wave detector to review the effect from the fluctuation of wave dark matter. There have some phase of gravitational wave, right?
Yeah.
So I want to know what's the background of that background. Is there some background?
What do you mean by background here?
I mean, is there another source to generate such a single?
Yeah, that's a great question. So, well, in the case of particle compressed halo, you can also do the same thing. In the case of wave compressed halo, you can do the same thing, although the pattern at which the waveform changes are different. And also, people have studied this kind of dephasing in the context of super radiant cloud. So if the central black hole is kind of rotating, there could be super radiant instability, such that whenever the companion object enters in the super radiant cloud, there could also be unique patterns of dephasing. Now the question is whether we can distinguish different kinds of the scenario, and that pretty much depends on the parameter space and also the sensitivity of the detector. In some cases, you can distinguish them. In some cases, maybe not.
Okay, thanks.
Okay, if there are no more questions, I think we can thank again Professor Kim. Thank you very much for your very nice talk, and
Thank you.
thanks
for
accepting the invitation.
Very nice talk.
Thank you.
See you next time.
Okay, bye-bye.
Yeah. Bye.